revision video for the space part of P1 for my class. So we'll start with structure of the universe. Well, from Aristotle's time, the early Greeks, 2,500 years ago, we assumed that the Earth was in the centre. And to be fair, why not? It looked pretty flat to us. Everything seemed to go around us, and so incorrectly we assumed the moon, the sun, and the planetos, the wandering stars, we now call them planets, all orbited the Earth. People, though, were getting a bit unhappy with this. When you plot the stars' locations through the night sky, you realise that centre of the Earth doesn't account for how the planets appear to move. So, Copernicus promoted an idea called the heliocentric model, sun-centred, which proposed that in fact the sun was in the centre and the Earth was one of many planets orbiting it. However, some people didn't like this idea, and so they eventually tried to stop it. And it was the observation by a scientist called Galileo that the Jovian moons, and every night he drew those moons with the invention of the telescope, finally showed that something was orbiting something else that wasn't the Earth, and hence that was the first kind of chink in the armour of the geocentric model, and it went on to later prove the heliocentric model. We now know that we live in a galaxy. We orbit a very average star, and if I move across I can show you. Our star is very average. We are a planet that is in the habitable zone of that star, and in the last 15 years we've discovered close to 1,000 other exoplanets, stars orbiting other stars, planets orbiting other stars. So if we zoom out, we are part of 4 planets that are called the inner planets, and that's separated by this region called the asteroid belt. And then we have the 4 gas giants. Pluto was demoted in 2006. It's now known as one of many Kepler objects that exist in this very ancient region of the solar system. It was the original debris as the solar system formed, and we now know there are at least 3 other bodies the same size, if not bigger than Pluto, out there. For this reason it was demoted down to a dwarf planet. If we move out, it takes like 4 years to shine then from the next closest star. In fact, it's a triple star system: Alpha Centauri, Proxima, and Alpha Beta. And this is our local neighbourhood. All of these stars are within tens of thousands of billions of trillions of miles. And we move out and we realise we're in one of the spiral arms of our galaxy, which we call the Milky Way. The Milky Way spins, takes 200 million years to do one orbit, and in its centre we believe there is a supermassive black hole. We can plot the radial velocity of the orbit of stars close by, and in the centre there is something throwing stars around like confetti. So we're fairly confident that this supermassive black hole is in the centre, and we now believe that they're in the centre of all galaxies, and they're actually a bit like the seeding object for galaxies to cluster around. So that's the structure of our universe. Next, if we go to the next one, life of stars. Stars are born, stars die. They all start in a nebula. Gravity causes them to collapse into the very beginning, which is a protostar, and it'll have an associated disk of dust around it. It will be spinning, and eventually the core will reach such high temperature and pressure that eventually you will have fusion. So in the core, fusion is happening. The remaining debris will form the planets, and then what happens is down to the mass of the star. Our star is very average, as I've said, and so our star will do the following. It will eventually have run through fusing all the hydrogen in the core and move on to fusing the helium. It will grow in size to become a red giant. It will gobble up its inner planets, and eventually all that will be left are its gas giants in the outskirts there. It will eventually billow away and leave behind the white hot core, which will be many, many hundreds of millions of degrees. This white dwarf will eventually cool, and we will be left with a black dwarf. There are no black dwarfs in the universe at the moment because this takes many, many hundreds of billions of years to do, and our universe is only 14 billion years old, so early days yet. That, however, is not the fate of all stars. I said that the mass affects it. If we back up, and instead of it being a normal sized star, we're talking 4 times plus, then we end up with something quite special. These stars have enough gravity to go on fusing beyond helium, and so they form supermassive red giants. These supermassive red giants, when they run out of fuel, the core instantly turns off. The outer edges head inwards at close to the speed of light. It can take about 1,000th of a second for a star this size to explode. For comparison, there's the sun, so we're talking huge. They implode inwards with lots of kinetic energy and then ricochet outwards, causing a supernova. At the time of a star going supernova, it will emit more radiation than all the stars in its own galaxy, of which there's on average 100 billion stars. And in doing so, it will create all the elements in the periodic table. So you and I and everything you see on the planet Earth and all the planets around us were all formed from a supernova that happened about 5 billion years ago where you're sat. You are literally made of star stuff. What we then get depends again on the mass. If the core is collapsed enough, those protons and electrons that were whizzing around in the hydrogen-helium atoms, they're fused together and they form neutrons. We end up with a very unusual object composed entirely of neutrons. These things spin very quickly and they have a massive magnetic field, and so they whoosh out these huge powerful radio jets, and if those jets cut across the Earth, we detect them as a radio blip. And it was in the 60s a lady called Jocelyn Grace Brunel who discovered these as part of her PhD research, and for a while we thought they were an alien signal. We now know they're pulsars. The ultimate, though, is a collapse to infinite density, in which case you end up with a black hole. A black hole, a bit wrongly named as such, consists of a singularity, a point of infinite density in the centre, and then a region of space around it, of which, if you're on one side, the speed of light is enough to get away. If you're on the other side, speed of light is not enough to get away, and you fall in. And it's for this reason that a black hole appears black, and on the outside they look bigger than they really are. It's the singularity in the middle that's doing the damage. So that's life of stars. Life in the universe. One of the biggest questions we have is, are we alone? And up until 15 years ago, we only knew of the planets in our own solar system. We now know of at least 1,000, and probably this time next year we'll know of about 2,000 to 3,000. So the question is, where are they? Well, for life to exist, we're pretty sure it's going to need water. Water is nature's chemical, it's a nature's solvent, it mixes with everything. It's going to have to be in the liquid state, so that puts a confine on where we're going to find it. If we take the sun, then we know the region close to it is too hot, and so for that reason Mercury at 400 degrees and Venus at 400 degrees, they're going to be too hot. We know that further away it gets colder, and so from about Mars onwards, Mars being right on the edge of the habitable zone, we know it's too cold. And we live, surprise surprise, in just the right zone. We call this the habitable zone, or, for those fond of fairy tales, the Goldilocks zone. Over time, this Goldilocks zone moves around a star. As the Sun and all stars change temperature as they age, this habitable zone can move further away. And in about 1.5 billion years' time, our habitable zone will have moved out towards Jupiter. So, if you're around at the time, hop over towards Jupiter, get yourself on Europa or Ganymede, and you might be able to go surfing. So that's life in the universe. We are focusing all our attention now on exoplanets that are in habitable zones, and we found quite a few. But the real kind of breakthrough for us is there sign of intelligence? For that, we are setting up 40 years old now, we are using satellite dishes to search for radio signals broadcast by alien civilizations. The reasoning being that the EM spectrum is going to be discovered by any civilization with intelligence. I mean, even we found it. And so at some point they will have communicated with radio. Whether they do now or not, we don't know. We've been searching for 40 years and we've not found anything. However, we've only searched less than 0.1% of our own galaxy. And so we've still got quite a long way to go. Telescopes. We live at the bottom of a 60-mile deep, thick atmosphere. Keeps us safe. Problem is, it also keeps us away from all the EM waves coming in from space. So, just like having a big sheet of protective glass, the EM waves out in space are filtered. The really long waves can cut through radio, but then very specific waves of infrared are blocked. By fluke, maybe we would never have been curious about space at all, but the waves we see, the visible, cut through beautifully, so you can look up at the night sky and see it. An animal that sees in the infrared doesn't see stars. And so, for some of our telescopes, we need to be above our atmosphere. And so, 50 years ago, we launched satellites, and now we have a whole fleet of them looking at every EM wave in the spectrum. Other types of telescopes, the visible ones, are reflectors and refractors. I'll go into those in the next module because I don't like them. Reflectors and refractors. So from this we will take the idea that you can be on land for waves that cut through our atmosphere. You can be in space for waves that don't. Another added benefit, because something like Hubble is in space, and let's see if we can cut back to Hubble now. I think I'm pushing my luck with my iPad. There we go, and here we are. So let's see if we can get back over to Hubble. Hubble is an optical telescope. We've just said light can get through to the surface of the Earth. So the question is, why would you want to spend billions extra putting something up in space? Here we have the launch with the Space Shuttle Discovery. Space shuttles don't launch anymore. The Yanks have pulled the money for it. So the question is, why did you want to put an optical telescope in space? Well, above the atmosphere, there is no nighttime and daytime. If you put it in the right orbit, you can stay in the nighttime all the time. You also can point to any point in the sky, whereas here we're trapped by the northern hemisphere stars. You can also point at any point in the night sky, and you can leave it pointing at that space for the next 14 to 25 days. And when you're collecting light from the very edge of our universe, you need that kind of time to collect the very, very weak light that will be reaching your telescope. You're avoiding atmospheric disturbances, so there's no rippling effect. For a similar effect, lay at the bottom of a swimming pool looking up. That's what it looks like to Hubble if it was on the ground. And you're avoiding vibration. When you have got a telescope this sensitive, even a car running past a mile away is going to vibrate your mirror and mess up your measurements. So that's why you'd want to put an optical telescope up in space. Hubble's awesome. Next. I'm determined to try and crash this. Boom. Age of our universe. Hotly debated, and now we live in the time where we know very, very accurately the age of our universe. We know that for some reasons we're not sure of, maybe one of you will find out, the universe started from nothing, and then there was a bang. Or was there? Recent articles are showing that there is a possibility the Big Bang didn't happen, but for now let's just keep it simple, and there was. So, our universe went through a point of expansion that was faster than the speed of light, called inflation, and then it carried on growing. We are 14 billion years into that growth, and strangely enough, we thought by now it would be nice and level, or it would be slowing down, just like throwing a ball up in the air. It's going to slow down. We thought possibly there might even be a hint that it was going to crunch. But this was a shocker. Everything was moving away faster. Our universe is getting bigger at a bigger rate. We have no idea why. The people who discovered it won a Nobel Prize for it and were as shocked as the rest of the world on discovering it. So, how do we find evidence? There are two bits of evidence for the age of the universe. The first one is called redshift. To understand redshift, you need a few key ideas. One is that light is a wave. It has a wavelength, it has a frequency. Just like the keys on a piano, each key represents a different note, while in light, the long wavelength, for us, in the visible, is red, and at the very other end is violet. And that represents the visible spectrum that we can see with our own eye. Newton discovered that when he split light using a prism. However, Ritter discovered that you could go off to the left and discovered infrared. He did that by using a prism and moving his thermometer to different points, and eventually, when he went above red, he discovered even greater heating. And Ritter, did I say Ritter discovered infrared? It was Herschel, sorry. And Ritter discovered ultraviolet by using the same kind of idea, but this time with a chemical process, and again discovered that by moving off the bottom, he discovered ultraviolet. And the history of science has been finding the other ones: microwave, radio waves, ultraviolet, X-ray and gamma rays. So, with that in mind, we can now use this idea that light is a wave. If the object emitting the light is moving towards you, then the wave is compressed and it appears to look more blue. We call that blue shift. And if the object is moving away from you, it is stretched, and hence the colour stretches to the red. So, Edwin Hubble got hold of a telescope in the 1920s, looked up at the night sky. He looked at very faint smudges of light, discovered they were galaxies, that they were actually not stars, they were galaxies outside of our own galaxy, and that all the light from these galaxies was redshifted. So he discovered we live in an expanding universe. The galaxies themselves are not actually moving that fast. It is the space in between them that is expanding. Space is getting bigger. And if you held your two fingers apart for 1 trillion years, and you were around long enough, the space in between your fingers would get bigger, but it'd be so imperceivably small as to be unmeasurable. It's only when you're looking across the scale of the universe that you can see this effect. So don't worry, things aren't going to just start moving away from you anytime soon. So that's redshift. By knowing the velocity of these objects, and by calculating the distance of these objects, you can calculate the time that it's taken those objects to travel that distance, using speed as distance over time. And all the measurements matched up. Anything with a very, very long redshift was very, very far away. And there's always a record on to see who can spot the most redshifted object. And every couple of months you'll see it in science publications explaining that they found something even further away, which represents being closer to the very beginning of our universe. So that's redshift. The more stretched, the further away. The further away, the faster it's going. The faster it's going, the older it is, and the closer it is to the Big Bang. The other piece of evidence comes from the fact that hot objects, time, heat, temperature, hot objects get cold. It's kind of one of the first things you learn. Don't touch hot things. And the same is true for our universe. It started off hot. It's now about 4 degrees above absolute zero. Down here somewhere. So the question was, where is all this infrared radiation? Well, we searched for it, and we searched in vain. One reason being, a lot of the infrared radiation couldn't reach the surface of the air, If you remember, we talked a minute ago about telescopes. So we went up into space, started the space race. We still couldn't find it, and that's because of this redshift again. You wouldn't say redshift for this answer, but the infrared, as it left the edges of our universe from the Big Bang, that information started as infrared and eventually shifted into the microwave. And so in the late 70s, using a giant horn, we collected the microwaves and we matched them to a temperature, and we discovered that it matched our model of the early universe exactly. And right now we have telescopes that are measuring in space the cosmic background radiation, or cosmic microwave background radiation, not commercial mortgage backing security. Cosmic microwave background radiation. And it yields images of the baby universe. And every few years we release a new, more improved photograph. And this information is just like looking at a baby photograph of you lot. You start seeing features that are eventually going to ripple out and form the early galaxies. And so this is giving us clues at the forces that were acting very, very early on in the universe. And this data is going to be poured over for the next decade or so. So, that's the age of our universe. That concludes my video. It's by no means conclusive. It's 9 o'clock in the morning. I'm probably not thinking too straight because I haven't had enough tea. I'm going to have one more. Any questions, as always, come and grab me and find out. Bye-bye.